There is a place on Earth where a change of only a few degrees can begin a chain of events that reaches almost every continent. It is not marked by mountains, cities, or coastlines. It lies across the broad equatorial Pacific, where the ocean appears calm from above, yet is constantly moving vast amounts of heat beneath its surface. Most days, this part of the world attracts little attention. Cargo ships cross it, fishing fleets work its waters, satellites pass overhead without pause. To anyone looking from the deck of a ship, it can seem almost endless, with little to distinguish one horizon from the next. Yet, this quiet stretch of ocean stores more solar energy than any machine humanity has ever built could hope to contain. Every sunrise adds another small measure of warmth. Every trade wind gently rearranges that warmth, guiding it westward across thousands of kilometers of open sea. Beneath the waves, invisible currents continue their patient work, carrying heat through layers of water that rarely reveal what they are doing to those standing above them. For much of the time, this enormous system follows a familiar rhythm. The easterly trade winds blow steadily across the equator. Warm, surface water gathers toward the western Pacific near Indonesia and northern Australia. Along the coast of South America, colder water slowly rises from below, bringing nutrients toward the sunlight where microscopic marine life can flourish. It is a balance that supports entire ecosystems. Fish gather where nutrients are abundant, rainfalls where warm water fuels towering tropical clouds. Air rises over one side of the Pacific and sinks over the other, creating an atmospheric circulation that quietly helps organize weather far beyond the ocean itself. None of this feels dramatic while it is happening. The Pacific is simply breathing in the way it has for countless generations. But every few years, something begins to change. The winds that usually push warm water westward become weaker. Sometimes they weaken only slightly. Sometimes they relax for weeks. On other occasions, they falter for months. What seems like a subtle shift in the atmosphere allows the ocean to answer in its own slow language. Warm water no longer remains piled against the western Pacific. It begins to spread back toward the east, not as a giant wave crashing across the ocean, but as an immense movement of heat unfolding over weeks and months. Beneath the surface, the boundary separating warm upper water from colder depths gradually sinks in some regions while rising in others. The ocean starts redistributing energy it has quietly stored for years. Long before heavy rain falls over distant countries, long before farmers notice changing seasons, and long before grocery prices begin to respond, the Pacific has already begun rewriting the conditions that make those events possible. This is El Niño. The name has existed for centuries. Fishermen along the coast of Peru noticed that around Christmas, warm waters sometimes appeared unexpectedly, disrupting the rich fisheries they depended upon. Because these events often arrive near the celebration of the Christ child, they called the phenomenon El Niño. At the time, no one imagined that this local observations described one of Earth's largest climate oscillations. There were no satellites, no drifting buoys, no global weather models, only careful observation repeated across generations. The fishermen could not see the atmosphere stretching across the Pacific. They could not measure sea surface temperatures from orbit or detect slow-moving waves hidden hundreds of meters beneath the ocean. Yet they recognized a pattern because their lives depended upon it. The fish behaved differently. The water felt warmer. The familiar rhythm of the sea had changed. Centuries later, modern science would discover that those local experiences were connected to an enormous system, linking ocean and atmosphere into a single conversation. Neither controls the other completely. Instead, each constantly responds to the other. The winds shape the ocean reshapes the winds. Small differences reinforce themselves until an entirely different state emerges. Climate scientists call this the El Niño Southern Oscillation. often shortened to ENSO. It is not simply an ocean event. It is not simply an atmospheric event. It is a partnership between the two. Understanding that partnership changes the way we think about weather itself. Storms may appear local. Floods may happen within a single river basin. Heat waves may settle over one nation, while another experiences unusual cold. Yet many of these seemingly disconnected events are influenced by patterns that began months earlier, over open water thousands of kilometers away. The atmosphere remembers. The ocean remembers even longer. Water absorbs heat far more slowly than air, but it also releases that heat more gradually. In many ways, the oceans serve as Earth's long-term memory, storing energy accumulated through seasons, and sometimes returning it months later under entirely different conditions. That delayed release explains why the greatest consequences of El Niño often arrive long after the first warming appears across the Pacific. By the time many people first hear that an El Niño has developed, the system responsible has already been quietly organizing itself beneath the surface for months. The first signs rarely appear where most people live. Instead, scientists notice subtle changes spread across thousands of observations. A drifting buoy records slightly warmer temperatures than expected. A research vessel measures a deeper layer of warm water below the surface. Satellite instruments detect tiny differences in sea level because warmer water occupies slightly more volume than colder water. Weather balloons observe changing wind patterns high above the equator. Individually, none of these measurements seems remarkable. Together, they begin telling the story of a planet adjusting its balance. Today, thousands of instruments contribute to this picture every hour. Networks of moored buoys stretch across the tropical Pacific, continuously recording temperature, winds, humidity, and ocean currents. Satellites circle overhead, mapping sea surface temperatures with remarkable precision. Autonomous floats rise and sink through the upper ocean, quietly collecting information from places no research ship could visit often enough. The result is not a prediction based on intuition. It is a constantly evolving portrait of a living planetary system. Even so, forecasting El Niño remains one of climate science's greatest challenges. The Pacific is vast. Its interactions unfold across enormous distances. Tiny differences today can influence rainfall patterns many months from now, yet countless additional processes continue shaping the outcome along the way. Scientists do not forecast a single storm 6 months into the future. Instead, they estimate how the background conditions of the entire climate system are likely to evolve. It is rather like recognizing that an orchestra has begun changing key before any individual instrument has completed the melody. The earliest notes may seem almost unchanged. Only later does the entire composition reveal that it has become something different. Earth's climate behaves in much the same way. The first changes are subtle, then more systems begin responding. Eventually, regions separated by oceans begin experiencing weather connected through processes few people ever witness directly. The remarkable part is not that El Niño changes weather. The remarkable part is that one ocean can influence so many places without ever leaving its own basin. This journey begins there, not with floods or droughts, not with headlines or records, but with the quiet movement of heat beneath the surface of the Pacific, where one of Earth's most influential conversations has already begun. Far below the rolling surface of the Pacific, where sunlight fades into cooler blue water, the story of El Niño begins long before satellites detect warmer temperatures from space. The most important movement is not something visible from a ship or an airplane. It unfolds beneath the surface, hidden inside the structure of the ocean itself. To understand why, it helps to imagine the upper Pacific not as one continuous body of water, but as layers. Near the surface, lies a broad blanket of warm water, heated every day by tropical sunlight. Below it rests a much colder layer that has remained largely isolated from direct warming. Between them is a transition zone where temperatures fall rapidly over a relatively short depth. Oceanographers call this boundary the thermocline. Although invisible, the thermocline acts almost like a movable floor beneath the warm ocean. When it rises closer to the surface, colder water can more easily reach sunlight through a process known as upwelling. When it sinks deeper, that colder water remains trapped below while the surface retains more heat. For much of a normal year, the trade winds help maintain this arrangement. As they blow from east to west across the equator, they gently push the warm surface layer toward Indonesia. The ocean range responds by allowing colder water to rise along the coast of Ecuador and Peru, replacing the water carried away by the winds. This exchange performs two jobs at once. It keeps the eastern Pacific relatively cool, and it continually delivers nutrients from the deep ocean into sunlit waters. Those nutrients are tiny, mostly nitrogen, phosphorus, and other dissolved minerals, but they sustain enormous populations of microscopic phytoplankton. These drifting organisms capture sunlight, forming the foundation of one of the richest marine food webs on Earth. Small fish feed upon them. Larger fish feed on those smaller fish. Seabirds, marine mammals, and eventually people become part of the same chain. One subtle movement of water supports an ecosystem extending from invisible microorganisms to entire fishing economies. Then the balance begins to shift. Sometimes the trade winds weaken gradually. On other occasions, brief bursts of westerly winds appear over the western Pacific, temporarily blowing in the opposite direction from what is expected. These wind bursts may last only days, yet they can trigger movements inside the ocean that continue for months. Instead of piling warm water farther west, the altered winds allow part of that stored heat to move back toward the central and eastern Pacific. It does not travel like a breaking wave. It travels as a broad pulse within the ocean itself. Scientists call this movement a downwelling Kelvin wave. Unlike familiar surface waves created by wind, a Kelvin wave moves along the equator while disturbing the depth of the thermocline beneath it. As it travels eastward, it gently pushes the warm upper layer downward, deepening the thermocline over thousands of kilometers. The change is remarkably smooth. There are no towering walls of water, no dramatic swells visible from the deck of a ship. Instead, the ocean quietly rearranges where its heat is stored. Because warmer water expands slightly, satellites measuring the height of the sea can sometimes detect these hidden changes. The ocean's surface may stand only a few centimeters higher than usual, yet that slight increase signals that an enormous amount of heat has accumulated beneath. What appears insignificant from space can represent an immense transfer of energy. By the time one of these Kelvin waves reaches the eastern Pacific, conditions near South America have already begun to change. The thermocline lies deeper than before. Upwelling becomes less effective. Colder water struggles to reach the surface. Sea surface temperatures gradually climb. For marine life, this is far more than a simple increase in temperature. Without steady upwelling, fewer nutrients reach the upper ocean. Phytoplankton populations may decline. Fish that depend upon those microscopic plants begin searching elsewhere for food. Predators follow. Entire ecological relationships begin shifting, sometimes over surprisingly short periods. Along the coast of Peru, generations of fishermen learned to recognize these changes long before modern instruments existed. They did not know about thermoclines or Kelvin waves. They noticed that familiar fishing grounds produced smaller catches. Species appeared later than expected or moved farther offshore. The sea itself behaved differently. Today, scientists can watch many of these processes unfold in near real time. Moored buoys anchored across the equatorial Pacific continuously measure temperatures from the surface down through hundreds of meters of water. Every reading contributes another piece to a picture that stretches across nearly half the planet. Research vessels periodically cross the same waters, lowering instruments through the ocean to record its structure in remarkable detail. Autonomous Argo floats drift with ocean currents before descending deep below the surface. After collecting temperature and salinity measurements, they slowly rise again, transmitting their observations to satellites before beginning another cycle. Together, these instruments reveal that the Pacific is never truly still. Even during years without a major El Niño, heat is constantly being stored, released, transported, and redistributed. The difference during El Niño is not that the ocean suddenly becomes active. It is that familiar patterns become reorganized on a much larger scale. The atmosphere notices. Warm ocean water increases evaporation. More water vapor enters the air. As moist air rises above the warmer surface, towering clouds become more likely to develop farther east than usual. Rainfall patterns begin shifting away from their typical locations. Areas that often receive abundant tropical rain may become unusually dry. Regions that are normally much drier can suddenly experience repeated storms. These changes are not isolated weather events. They represent a reorganization of one of Earth's largest circulation systems. Meteorologists refer to this shifting pattern as part of the Walker circulation, a vast loop of rising and sinking air stretching across the tropical Pacific. During neutral conditions, rising air over the western Pacific helps support heavy rainfall across Indonesia and surrounding regions, while descending air dominates farther east. As El Niño develops, that balance weakens. The rising branch of the circulation drifts eastward. Clouds follow, rain follows. So do changes in atmospheric pressure that extend well beyond the tropics. The ocean has not simply warmed. It has begun speaking differently to the atmosphere. Every conversation between ocean and sky influences another. Jet streams shift. Storm tracks migrate. Some regions experience fewer storms than expected. Others receive far more than their seasonal average. Yet all of these distant outcomes remain connected to something almost impossible to see without specialized instruments: the slow movement of heat beneath the Pacific Ocean. It is one of the quietest processes in climate science and one of the most influential. If the Pacific Ocean were the only place affected by El Niño, it would remain an important subject for oceanographers, but not for much of the rest of the world. What makes El Niño remarkable is that its influence refuses to stay where it begins. Once the atmosphere adjusts to the warmer Pacific, waves of changing pressure and wind begin traveling far beyond the tropics. These are not waves in the ocean, but broad atmospheric surfaces that ripple through the jet streams guiding storms across the northern and southern hemispheres. The Pacific does not send storms across continents. Instead, it changes the pathways those storms are likely to follow. Imagine standing beside a river. A fallen tree placed upstream does not create new water. It simply redirects where the water flows was. Some channels receive more, others receive less. Downstream, the landscape begins changing because the river has chosen different routes. The atmosphere behaves in much the same way. The jet streams are fast-moving rivers of air, several kilometers above Earth's surface. They help separate warm and cold air masses while steering weather systems across entire continents. Even a modest shift in their position can alter where rain falls, where snow accumulates, and where prolonged dry periods develop. During many El Niño events, the subtropical jet stream across the Pacific becomes stronger and shifts farther south. Winter storms that might otherwise remain over the northern United States are more likely to sweep across California, the Southwest, the Gulf Coast, and parts of the southeastern states. Farther north, a different pattern often emerges. The Pacific Northwest may experience fewer storms. The northern Rockies can receive less mountain snowfall. Much of Canada and the northern tier of the United States frequently experience milder winter temperatures than average. These are tendencies rather than guarantees. No single El Niño produces exactly the same weather. Local conditions, other climate patterns, and ordinary weather variability continue shaping each season. A powerful snowstorm can still strike during an El Niño winter. A dry month can still occur, where wetter conditions are generally expected. Climate patterns influence probabilities. They do not eliminate uncertainty. That distinction is one of the most important ideas in modern meteorology. Forecasting climate is different from forecasting tomorrow's weather. A seasonal outlook does not attempt to predict the exact day rain will fall or the precise temperature on a particular afternoon. Instead, it estimates whether the coming months are more likely to lean toward wetter, drier, warmer, or cooler conditions than history would normally suggest. For many people, those probabilities quietly shape decisions long before any clouds appear. Reservoir managers decide how much water to release. Electric utilities estimate future demand. Farmers consider planting schedules. Emergency planners review flood maps. Insurance companies assess seasonal risk. The atmosphere may still be changing high above the Pacific, but its influence has already begun reaching meeting rooms, farms, and communities thousands of kilometers away. One of the clearest examples appears in Western North America. California often enters public conversations whenever El Niño develops. The reason is understandable. Water has always been one of the state's defining challenges. Its climate depends heavily upon a relatively small number of winter storms. Those storms refill reservoirs, build mountain snowpack, recharge groundwater, and provide water that will later support cities, agriculture, and ecosystems through the long dry season. When several winters pass with limited precipitation, concern naturally grows. Reservoirs decline, snowpack shrinks. Groundwater is pumped more heavily. Wildfire risk often increases as vegetation dries. In that context, forecasts of a wetter El Niño winter can sound encouraging. More rain seems like an obvious solution, yet water arriving too quickly can become as difficult to manage as water that never arrived. A series of powerful atmospheric rivers crossing the Pacific may deliver extraordinary amounts of moisture within only a few days. If soils have already become saturated, additional rainfall has fewer places to go. Rivers rise rapidly. Urban drainage systems struggle to keep pace. Hillsides weakened by previous wildfires may become vulnerable to landslides and debris flows. Meanwhile, higher mountain temperatures introduce another complication. Winter precipitation that would normally fall as snow may instead fall as rain at elevations that historically stored water safely until spring. Snowpack acts as a natural reservoir. It captures winter moisture and releases it gradually as temperatures rise. Rain behaves differently. It runs downhill almost immediately. Two winters may receive similar amounts of total precipitation while producing very different long-term water supplies. One stores water, the other simply moves it. Farther north, reduced snowfall can quietly reshape entire river systems. Communities depending upon spring snowmelt may discover that rivers peak earlier in the year and decline sooner during summer. Hydroelectric facilities adjust operations. Irrigation districts reconsider water allocations. Cold water habitats supporting fish experience different seasonal flows. Many of these changes unfold slowly enough that few people notice them day by day. Only months later, when reservoirs remain lower than expected, despite a seemingly wet winter, does the broader pattern become visible. El Niño rarely acts through one dramatic event. Its influence accumulates through many connected adjustments, each appearing modest on its own. A stronger storm track here, a warmer winter there, less snow in one mountain range, more rainfall across another watershed. Taken separately, each seems manageable. Taken together, they begin reshaping the movement of water across an entire continent. And North America is only one chapter in a much larger story. While one side of the Pacific experiences changing winter storms, nations thousands of kilometers away may be entering unusually dry seasons, weaker monsoons, or shifting patterns of tropical rainfall. The same redistribution of heat that changes a California winter can also alter planting seasons in Southeast Asia, fisheries along South America's Pacific coast, and rainfall across parts of Africa and Australia. The Pacific does not choose winners or losers, it simply redistributes energy. The atmosphere responds, the continents respond, and eventually, so do the people living beneath those changing skies. Long before anyone notices higher prices at the grocery store or reads about a disappointing harvest, the first signs often appear in places where rain has quietly failed to arrive. The atmosphere has no concern for political borders. It does not recognize planting calendars or harvest deadlines. It simply carries moisture where the changing circulation allows, leaving some regions with more rain than they expected, and others with far less than they need. For agriculture, timing is often more important than the total amount of rainfall. A field may receive exactly the average amount of precipitation over an entire year and still produce a poor harvest if that rain falls at the wrong moment. Seeds require moisture to germinate. Young plants need stable conditions to establish roots. Flowering crops depend upon carefully timed rainfall and moderate temperatures. Grain must mature under a different balance of sunlight, warmth, and dryness. Missing only one of those windows can reduce an entire season's production. This is why El Niño cannot simply be described as bringing more rain or less rain. It changes when water arrives. It changes where clouds develop. It changes how long dry periods last, and those subtle differences ripple through some of the world's most productive farming regions. Across parts of Southeast Asia, seasonal rainfall depends heavily upon the annual monsoon. These winds reverse direction with the changing seasons, carrying enormous amounts of moisture inland from surrounding oceans. Millions of farmers have built their agricultural traditions around this dependable rhythm. Rice fields are planted with remarkable precision. Communities have learned, generation after generation, to work alongside the expected arrival of seasonal rains. During many El Niño years, however, the atmosphere reorganizes that rhythm. The monsoon may arrive later than usual. It may produce fewer periods of sustained rainfall, or it may become less evenly distributed, alternating between dry spells and sudden downpours. None of these outcomes guarantees crop failure. Modern irrigation, improved crop varieties, and careful water management have increased resilience in many regions. Yet even modest reductions in rainfall can place additional pressure on farmers already balancing uncertain weather with growing demand. Australia often experiences a different challenge. Large portions of the continent are naturally dry, and agriculture there frequently depends upon a limited number of favorable rainfall events during the growing season. When El Niño shifts atmospheric circulation, those rains sometimes become less reliable. Winter grain crops may establish more slowly. Pastures can support fewer grazing animals. Reservoirs supplying irrigation systems may receive less inflow than expected. For wheat producers, every missing week of moisture becomes part of a much larger calculation. One farm may lose only a small percentage of its harvest. Another may perform close to average. But when similar conditions extend across wide agricultural regions, the combined reduction becomes visible in global markets. South America presents another layer of complexity. Along the Pacific coast, Warmer surface waters reduce the upwelling that normally supports one of Earth's richest marine ecosystems. For centuries, cold water rising from the deep has carried nutrients toward the surface, feeding enormous populations of anchoveta. These small fish are rarely noticed outside scientific circles, yet they occupy an essential position within the global food system. Much of the catch is processed into fish meal. That product becomes a valuable source of protein for aquaculture and livestock feed around the world. When warmer waters reduce anchoveta populations or push them into deeper offshore habitats, fishing fleets often land small catches. The effect is rarely immediate for consumers. Feed manufacturers adjust inventories, producers search for alternative ingredients. Markets gradually absorb higher costs. Only much later do those changes become visible through the prices of farmed seafood, poultry, or pork. Elsewhere, coffee trees continue growing almost unnoticed on tropical hillsides. Cocoa pods slowly develop beneath dense forest canopies. Sugarcane reaches upward through warm air. Each crop depends upon its own delicate balance of temperature and rainfall. Coffee blossoms, for example, emerge after carefully timed moisture. Too little rain delays flowering. Too much rain during sensitive periods may reduce pollination or encourage disease. Cocoa responds differently. Excessive heat can place trees under stress. Extended drought may reduce the number of pods reaching maturity. Sugarcane generally tolerates warm conditions well, yet prolonged dryness during key stages of growth may limit yields. No single weather event determines the outcome. Agriculture is rarely governed by one day or even 1 week. Instead, harvests reflect months of accumulated conditions. Farmers understand this instinctively. They do not judge a season after one afternoon's rain. They watch the soil. They observe the leaves. They notice subtle changes in flowering, insect activity, groundwater, and the pace of plant growth. Many of those observations are now reinforced by satellites, orbiting hundreds of kilometers overhead. From space, scientists monitor vegetation health, soil moisture, surface temperature, and even tiny changes in plant productivity across entire continents. A field that appears green from the roadside may already reveal signs of stress through wavelengths invisible to the human eye. These observations help governments, researchers, and humanitarian organizations recognize emerging risks before harvest statistics are available. Even then, uncertainty remains. A favorable rainstorm arriving at the right moment can rescue part of a growing season. An unexpected heat wave can erase weeks of earlier optimism. Climate creates the background. Weather writes the final details. That distinction explains why forecasts are expressed as probabilities rather than certainties. Scientists are not predicting the fate of a single farm. They are estimating how likely it is that broad environmental conditions will favor or challenge agricultural production across entire regions. For the global food system, those probabilities matter enormously. Modern agriculture is deeply interconnected. A bakery in Europe may rely on wheat grown in Australia. Seafood raised in northern waters may depend upon feed ingredients originating along the coast of Peru. Chocolate factories purchase cocoa harvested thousands of kilometers away. Coffee roasted in one country may have crossed several oceans before reaching a local cafe. Most consumers never see those connections. Products arrive neatly packaged on familiar shelves. The journey behind them remains largely invisible only when weather begins reshaping harvests across multiple continents. At the same time, do those hidden links become easier to recognize? The Pacific has not changed every field. It has simply altered enough of them that the world's agricultural network begins adjusting in response. Like threads within an enormous woven fabric, individual harvests support one another. When tension develops in several places at once, the entire pattern subtly shifts. And before long, those distant fields will begin influencing decisions made in shipping ports, commodity exchanges, food manufacturers, and eventually, kitchens far removed from the Pacific Ocean where the story first began. By the time a harvest is smaller than expected, the weather that caused it is often already fading into memory. Fields are harvested. Fishing boats return with lighter catches. Reservoirs settle into new seasonal levels. The skies above may even appear perfectly ordinary again. Yet the consequences are only beginning their journey. Modern food does not travel directly from a farm to a dinner table. It moves through one of the most intricate supply systems humanity has ever created. A shipment of wheat harvested on one continent may become flour in another. Palm oil extracted in Southeast Asia may be blended into products manufactured thousands of kilometers away. Soybeans, rice, seafood, coffee, cocoa and sugar all move through networks of ports, railways, processing plants, financial markets, and distribution centers before reaching the shelves of local stores. Most of the time, this system operates with remarkable efficiency. Its complexity allows supermarkets to remain stocked throughout the year, even when products originate on opposite sides of the planet. Consumers rarely think about where each ingredient began its journey. They simply expect familiar products to remain available. That expectation is supported by an enormous amount of planning happening quietly behind the scenes. Harvest forecasts are updated constantly. Shipping companies adjust their schedules months in advance. Food manufacturers negotiate contracts long before crops are harvested. Retailers estimate future demand while warehouses balance inventories across entire regions. Every decision depends upon information flowing as smoothly as the goods themselves. When El Niño begins affecting multiple agricultural regions at the same time, those calculations gradually become more difficult. Not because the world suddenly runs out of food, but because uncertainty begins replacing confidence. Imagine a grain exporter watching weather forecasts from several producing countries. One region expects lower rainfall. Another reports unusually high temperatures. A third is experiencing delayed planting after unexpected flooding. None of these developments guarantees a poor harvest, yet together they increase the possibility that future supplies may become tighter than expected. Markets respond not only to what has already happened, they also respond to what appears increasingly likely. This is one reason commodity prices sometimes begin moving before combines have entered the fields. Buyers are not purchasing only today's harvest, they are purchasing expectations about tomorrow's. If those expectations change, prices often change first. This process is neither irrational nor unusual. It is an attempt to manage uncertainty. A food manufacturer producing breakfast cereal, for example, cannot wait until every wheat harvest is complete before deciding how much grain to purchase. Factories require steady supplies. Employees continue working. Transportation schedules continue operating. Planning months ahead becomes essential. When uncertainty grows, many companies choose to secure supplies earlier than usual. Others increase inventory as a precaution. Still, others diversify purchases across multiple regions. Each individual decision appears reasonable. Collectively, however, they increase competition for available supplies. The market begins tightening before any actual shortage exists. Sometimes, the psychological response becomes nearly as influential as the environmental one. History has shown that expectations themselves can reshape markets. If traders believe future harvests may decline, they often compete more aggressively for existing inventories. Prices rise. Additional buyers enter the market, hoping to avoid even higher costs later. Those actions create new signals that other participants also begin responding to. The cycle reinforces itself. Most of the time, markets eventually settle. as better information becomes available. Actual harvest data replaces speculation. Conditions become clearer. But during periods when weather remains uncertain across several major producing regions, volatility often persists much longer. Governments occasionally become part of this story as well. When domestic food prices begin rising, political leaders face difficult choices. Their first responsibility is usually the stability of food supplies within their own countries. If harvests appear uncertain, some governments may reduce exports, introduce temporary restrictions, or encourage larger domestic reserves. From their perspective, these measures are intended to protect local consumers. Keeping more grain or rice inside national borders may help slow domestic price increases. Yet international markets experience those decisions differently. Every shipment withheld from export slightly reduces the amount available to importing countries. Nations that depend heavily upon imported food begin searching for alternative suppliers. Competition increases. Prices respond once again. This does not necessarily indicate that the world lacks enough food overall. It often reflects how food is distributed. Some regions produce far more than they consume. Others rely heavily upon international trade. When weather affects several exporting regions simultaneously, those existing relationships become more sensitive. The interconnected nature of the global food system becomes increasingly visible. For consumers, however, these international adjustments remain almost invisible. The supermarket still opens every morning. Delivery trucks continue arriving. Most familiar products remain available. Changes often begin quietly. A promotional discount disappears. A package becomes slightly smaller, while its price remains unchanged. A favorite brand is temporarily unavailable. Restaurants revise menus. Manufacturers substitute ingredients where practical. Only over time does the broader pattern emerge. Food inflation rarely announces itself through empty shelves. More often, it arrives through gradual adjustments that accumulate month after month. A family may hardly notice one additional dollar spent on cooking oil. Another few dollars for bread seems manageable. Coffee becomes slightly more expensive. Frozen meals increase in price. Fresh produce fluctuates with the season. Each individual change appears modest. Together, they reshape household budgets. The effects are rarely distributed equally. Communities already spending a large share of their income on food experience those increases more sharply than wealthier households. For some families, higher prices require little more than choosing different brands. For others, they influence nutrition, meal planning, and financial security. In this way, an ocean pattern that began thousands of kilometers away gradually reaches kitchen tables without ever appearing on the evening weather forecast. The Pacific does not send waves into supermarkets. It sends signals through harvests. Harvests influence markets. Markets influence prices. And prices quietly become part of everyday life. The remarkable part is not that these connections exist. It is that they are often invisible until enough of them begin moving together. Only then does the full scale of Earth's interconnected systems become easier to appreciate. The atmosphere, the ocean, agriculture, transportation, economics, and daily life are not separate stories. They are different chapters within the same unfolding process. By now, the influence of El Niño has traveled far from the equatorial Pacific. It has shifted rainfall. It has altered harvests. It has quietly affected supply chains that connect continents. Yet one of its most profound effects unfolds much higher above the ocean, in a place no one can see from the ground. It happens in the atmosphere itself. Every second, Earth is exchanging energy with space. Sunlight arrives, warming oceans, forests, deserts, and cities. The planet then releases part of that energy back outward as infrared radiation. Under ordinary conditions, This exchange remains remarkably balanced over long periods of time. Small fluctuations occur every day, every season, and every year. But the climate system is constantly working toward equilibrium. The ocean plays a central role in that balance. Although the atmosphere often captures our attention, it contains only a small fraction of the excess heat accumulating within Earth's climate system. More than 90% of that additional heat has been absorbed by the oceans. For decades, the Pacific has quietly stored enormous amounts of thermal energy beneath its surface. Most of that heat does not immediately warm the air above our heads. Instead, it remains locked within the upper layers of the sea, moving slowly through currents that circle the globe. El Niño changes that relationship as warm water spreads eastward across the tropical Pacific. Evaporation increases. More water vapor enters the atmosphere. Warm, moist air rises more readily, fueling extensive cloud systems and thunderstorms. These towering clouds do more than produce rain. They become powerful engines, transporting heat upward through the atmosphere. Energy that had remained stored within the ocean begins entering the air on a much larger scale. This transfer does not happen overnight. It unfolds gradually, often over many months. That delay explains one of the most misunderstood aspects of El Niño. The warmest global temperatures do not always occur at the exact moment when ocean temperatures reach their highest point. Instead, the atmosphere continues, responding even after the ocean has begun changing again. The climate system has momentum. Just as a large ship continues moving after its engines slow, Earth's oceans and atmosphere continue exchanging energy long after the initial warming has developed. Scientists have observed this pattern repeatedly. Major El Niño events are often followed by periods of unusually high global average temperatures. The relationship is not perfect. Every event is influenced by additional climate processes. Volcanic eruptions, regional weather patterns, ocean circulation outside the Pacific, and long-term climate trends all contribute to the final outcome. Nevertheless, the broad connection has become one of the most carefully studied features of the climate system. It is important, however, to distinguish between weather and climate. A warm global average does not mean every location experiences unusual heat. Some regions may actually become cooler than average for part of the year. Others may receive persistent cloud cover that limits daytime warming. Global temperature represents the average condition of an entire planet, not the experience of any single neighborhood. This distinction often disappears in public discussion. People naturally compare climate change with yesterday's weather. If one afternoon feels unusually cool, it can seem difficult to imagine that global temperatures remain elevated. Yet, climate operates on vastly larger scales. A single weather station tells only one small part of the story. Thousands of observations collected across land, sea, and atmosphere reveal the broader picture. In recent decades, another factor has become increasingly important. The background climate itself has changed. Human activities, particularly the release of greenhouse gases, have gradually increased the amount of heat retained within Earth's climate system. This long-term warming does not replace natural climate cycles such as El Niño. Instead, the two interact. One provides the baseline, the other temporarily shifts conditions above or below that baseline. An analogy may help. Imagine standing on a gently rising hillside while also walking over rolling waves. The hill represents the long-term warming trend. The waves represent natural climate variability. You continue moving up and down with each wave, but the entire landscape beneath you is slowly rising as well. During a strong El Niño, those two influences may briefly align. Natural warming adds to the already elevated baseline. As a result, global temperatures may reach levels that would have been much less likely several decades ago. Scientists continue studying exactly how these interactions evolve. Climate is one of the most complex systems ever examined. No single event explains every outcome. No single mechanism determines every future season. Careful observation remains essential. Thousands of researchers around the world compare satellite measurements, ocean observations, atmospheric records, ice cores, tree rings, coral archives, and sophisticated computer simulations to better understand these connections. Each new El Niño becomes another opportunity to learn, not because nature is repeating itself exactly, but because every event occurs under slightly different background conditions. The Pacific changes, the atmosphere changes, the planet itself changes. Together, they create combinations that have never existed in precisely the same way before. Perhaps that is one of the quiet lessons hidden inside El Niño. Earth is not a collection of isolated systems. The oceans do not operate independently of the atmosphere. Clouds do not exist separately from sunlight. Forests, rivers, glaciers, fisheries, farms, cities, and coastlines all participate in an ongoing exchange of energy that has continued for millions of years. Most of the time, these exchanges remain invisible. The world simply feels normal. Rain falls, rivers flow, ships cross the oceans, seasons arrive one after another. Only occasionally does a phenomenon like El Niño reveal just how deeply connected those familiar experiences have always been. It reminds us that the climate is less like a machine with separate parts and more like a conversation that never truly ends, one voice answering another, across oceans, continents, and the atmosphere itself. For most of human history, El Niño arrived without warning. Fishing communities noticed unusual waters. Farmers waited for rains that never came. Merchants wondered why harvests had failed in places they would never see. Each society observed only a small part of a much larger system. The connections between those distant events remained hidden. Today, that has changed. Long before the atmosphere finishes responding, scientists are already watching the Pacific with extraordinary precision. From hundreds of kilometers above Earth, satellites measure the temperature of the ocean's skin. Others monitor the height of the sea surface with radar accurate enough to detect differences of only a few centimeters. Those tiny variations reveal where warm water has expanded, quietly identifying reservoirs of heat moving beneath the surface. Across the equatorial Pacific, a network of moored buoys records conditions every hour. Each buoy measures sea temperature from the surface downward through multiple depths. It also observes wind speed, air pressure, humidity, and the exchange of heat between the ocean and the atmosphere. Individually, each instrument tells a local story. Together, they describe the evolving state of nearly half the world's largest ocean. Autonomous Argo floats add another remarkable perspective. Unlike anchored buoys, these instruments drift with ocean currents. Every several days, they descend hundreds or even thousands of meters below the surface before slowly rising again. As they return upward, they collect detailed measurements of temperature and salinity throughout the water column. Once they reach the surface, they transmit their observations to satellites before beginning another cycle somewhere else in the global ocean. Thousands of these silent observers now operate across nearly every major ocean basin. Many people imagine climate science as relying mainly upon computer simulations. In reality, those simulations depend first upon observation. Without measurements, even the most sophisticated model cannot describe the actual state of the Earth. Every forecast begins with data. Millions of individual observations flow into forecast centers each day. Weather stations, ocean buoys, ships, aircraft, weather balloons, research vessels, river gauges, satellite instruments. Each contributes another small piece of a planetary puzzle. Only after assembling that picture do scientists begin projecting how conditions may evolve over the coming weeks or months. The computer models themselves are remarkable achievements. Rather than predicting one storm in isolation, they solve mathematical equations describing how air and water move across a rotating planet. They account for sunlight, cloud formation, evaporation, radiation, ocean circulation, ice, mountains, and countless other physical processes interacting simultaneously. No model captures reality perfectly. Every model contains uncertainty. That is why forecasting centers around the world compare many simulations, instead of relying upon only one. If numerous independent models begin pointing towards similar conditions, confidence increases. If their projections diverge widely, forecasters become more cautious. This is why seasonal outlooks are usually expressed as probabilities. A forecast might indicate an increased likelihood of above-average temperatures or a greater chance of wetter than normal conditions. It is not promising that those outcomes will occur everywhere. It is describing how the odds have shifted. This approach can sometimes seem frustrating. People naturally prefer certainty. They want to know exactly how much rain will fall, or precisely how warm the coming winter will be. Nature rarely offers such precision months in advance. Instead, science provides something equally valuable. It reduces uncertainty. That difference matters enormously. A reservoir manager deciding how much water to store does not require knowledge of every future storm. Knowing that an unusually wet season has become more likely may already improve planning. Farmers selecting crop varieties benefit from understanding changing seasonal risks, even if individual rainfall events remain impossible to predict. Emergency agencies preparing flood response plans often begin months before the first storm forms. Utilities estimate future electricity demand. Shipping companies consider changing ocean conditions. Insurance providers evaluate seasonal hazards. Airlines review historical weather patterns while planning schedules. Many of these decisions occur quietly, long before the public notices changing forecasts. The better our understanding of El Niño becomes, the more time societies gain to prepare. Preparation does not eliminate risk. Floods may still occur. Droughts may still develop. Harvests may still disappoint. But advanced knowledge allows people to reduce some of the consequences. Perhaps this is one of science's greatest contributions. Its purpose is not to control nature. It is to understand nature well enough that people can make wiser decisions while living within it. Even now, many questions remain unanswered. Scientists continue investigating why some El Niño events become exceptionally strong, while others weaken unexpectedly. They study how warming oceans may influence future ENSO behavior. They examine interactions between El Niño and other climate oscillations that span the Atlantic, Indian, and Southern Oceans. Every new observation adds another layer of understanding. Every unexpected outcome becomes another opportunity to refine existing theories. In many ways, climate science resembles navigation across an immense ocean. Early explorers relied upon stars and experience. Modern navigators combine those traditions with satellites, precise maps, and constantly updated information. Neither generation controlled the sea. Both sought to understand it more completely. The Pacific still keeps many of its secrets. Its deepest waters remain largely unexplored. Its interactions with the atmosphere continue revealing new complexities. Yet each year, humanity learns to read its subtle signals with greater clarity. Not because the ocean has become simpler, but because our ability to observe, measure, and understand it continues to grow. And with every quiet measurement taken beneath the waves or high above the clouds, the conversation between Earth and those who study it becomes just a little easier to hear. If there is one lesson woven through every El Niño, it is that the Earth's climate does not operate on a human schedule. Governments plan in years. Businesses often think in quarters. Families organize life around seasons, school, calendars, and holidays. The climate measures time differently. The ocean may spend years storing heat before gradually releasing part of it over a single season. A mountain snowpack builds through months of winter, then supplies rivers well into summer. Forests respond to rainfall accumulated over decades. Coral reefs reflect changes that unfold across generations. When viewed from this wider perspective, El Niño is no longer simply an unusual weather event. It becomes one expression of a planet that is constantly redistributing energy. That redistribution has always existed. Long before cities, agriculture, or written history, the Pacific was already shifting heat from one region to another. Rainforests expanded and contracted. Deserts changed their boundaries. Coastlines experienced alternating years of abundance and scarcity. Human civilization developed within that natural, changing environment. Over time, however, civilization itself became increasingly interconnected. Food grown on one continent now feeds another. Electricity depends upon river systems whose flows vary from season to season. International trade assumes that ports remain open, shipping lanes remain reliable, and harvests remain reasonably predictable. As these connections have strengthened, societies have also become more sensitive to disruption occurring far away. A delayed monsoon in one region may influence food processing elsewhere. Reduced hydropower generation may increase demand for other energy sources. Changing fisheries affect coastal communities whose traditions have lasted centuries. The climate has always been connected. What has changed is the extent to which humanity depends upon those connections remaining stable. This realization has gradually transformed how scientists think about resilience. For many years, discussions focused primarily on predicting individual events. Would this winter be wetter? Would the coming hurricane season be quieter? Would one harvest exceed another? Those questions remain important. But today, researchers increasingly ask a broader one. How well can societies adapt when conditions become less predictable? Adaptation does not always require dramatic technological breakthroughs. Sometimes it begins with better observation. Reservoir systems can be managed more flexibly when seasonal forecasts improve. Farmers may diversify crop varieties to reduce dependence on one rainfall pattern. Cities can redesign drainage systems after understanding changing flood risks. Fishing communities may adjust harvesting practices as marine ecosystems shift. Engineers can strengthen infrastructure using updated climate information, rather than relying solely on historical averages. None of these measures prevents El Niño. Instead, they recognize that variability itself is part of the natural world. Perhaps one of the greatest misconceptions about climate is the belief that stability is its normal condition. In reality, Earth's environment has always been dynamic. Glaciers have advanced and retreated. Coastlines have risen and fallen with changing sea levels. Forests have migrated across continents. Species have adapted, relocated, or disappeared as environments evolved. Human societies often remember only the relatively short period reflected within written records. The climate remembers much longer. Ice cores drilled deep into Antarctica and Greenland preserve tiny bubbles of ancient air. Layer by layer, they reveal atmospheric conditions stretching back hundreds of thousands of years. Tree rings record wet years and dry years with remarkable precision. Lake sediments preserve traces of ancient floods. Coral skeletons quietly archive changes in ocean temperatures through their annual growth. Together, these natural archives remind us that today's observations belong to a much longer planetary story. Every El Niño becomes another chapter within that record. Each event differs slightly from those before it. Some remain relatively weak. Others reorganize weather across much of the globe, know to unfold in exactly the same way, because the Earth itself is never exactly the same from one decade to the next. That is why scientists continue observing, rather than assuming. Curiosity remains more valuable than certainty. Every new measurement offers an opportunity to refine understanding. Every unexpected outcome becomes part of the growing conversation between observation and theory. There is something quietly reassuring about this process. It reminds us that science is not a collection of final answers. It is an ongoing practice of paying close attention. The Pacific does not announce its intentions. It offers subtle signals, a slight warming of the surface, a gentle shift in prevailing winds, a deepening thermocline, a changing pattern of clouds near the equator. Individually, these signs seem almost insignificant. Together, they reveal the beginning of a transformation capable of influencing weather across much of the world. Perhaps that is the deeper lesson hidden beneath El Niño. Great changes often begin quietly, not with sudden drama, but with countless small adjustments accumulating until an entirely different pattern emerges. The ocean teaches patience, the atmosphere teaches connection, and together they remind us that the planet is constantly speaking in slow, measured rhythms that reward careful observation far more than hurried conclusions. As the journey through El Niño comes to a close, it becomes easier to see that this phenomenon is not simply a story about unusual weather. It is a story about connection, a connection between sunlight and seawater, between winds that blow across an open ocean and rivers flowing through distant valleys, between tiny marine organisms drifting beneath the surface and meals prepared thousands of kilometers away, between decisions made by nature over many months and decisions made by people every single day. For much of modern history, these relationships remained hidden. People experienced floods, droughts, storms, or failed harvests as separate events. Only gradually did science reveal that many of them shared a common beginning in the tropical Pacific. What once appeared to be isolated disasters slowly became recognizable as different expressions of the same planetary system. That realization has quietly changed the way humanity understands Earth. The planet is no longer viewed as a collection of separate oceans, continents, forests, and skies. Instead, it is increasingly understood as one continuous system where energy is constantly exchanged between land, sea, ice, and atmosphere. Nothing exists entirely alone. Warm water influences clouds. Clouds influence rainfall. Rainfall shapes rivers. Rivers nourish farms. Farms support cities. Cities depend upon decisions made by millions of people who may never realize that part of their daily lives has been influenced by conditions unfolding far beyond the horizon. There is a certain humility in recognizing this. Human civilization has learned to build remarkable technologies. Satellites circle the globe. Research vessels cross every ocean. Powerful computers simulate climate months into the future. Thousands of scientists collaborate across nations, sharing observations that would have been unimaginable only a few generations ago. Yet despite all of that knowledge, the Pacific still reminds us that nature operates according to its own rhythms. It cannot be instructed to produce rain exactly where it is needed. It cannot be persuaded to weaken a storm or strengthen a harvest. Understanding is not the same as control, and perhaps it never should be. The value of understanding lies elsewhere. It allows communities to prepare. It allows farmers to plan. It allows engineers to design more resilient infrastructure. It allows emergency managers to respond earlier. It allows governments to recognize risks before they become crises. Most importantly, it allows people to replace surprise with awareness. That may be one of science's quietest successes, not eliminating uncertainty, simply reducing it. Even after centuries of observation, El Niño continues to offer new questions. Researchers still investigate why some events intensify rapidly, while others remain moderate. They continue exploring how different ocean basins interact. They study the influence of changing background climate conditions on future El Niño behavior. Every event becomes another chapter in a record that is still being written. The Pacific is both familiar and mysterious. It follows physical laws that scientists understand remarkably well, yet the countless interactions within the climate system remain too rich, too dynamic, and too interconnected to be reduced to a simple formula. Perhaps that complexity is not something to fear, it is something to appreciate. The same processes that sometimes bring drought also sustain rainforests. The same ocean currents that occasionally disrupt fisheries have supported marine life for countless generations. Variability is not a flaw in Earth's design. It is one of the ways the planet continually redistributes energy, maintaining a balance that is always changing and yet remarkably enduring. If you could somehow rise high above Earth and watch many decades pass in only a few quiet moments, the familiar outlines of continents would remain almost unchanged. But the atmosphere would appear alive. Cloud bands would drift endlessly around the globe. Storms would form and dissolve. Ocean temperatures would slowly brighten and fade across the Pacific. Snow would spread across mountains before retreating once again. Forests would breathe with the seasons. Rivers would swell and shrink. Nothing would remain perfectly still. And yet, beneath all of that movement, there would be an unmistakable sense of continuity. The same sunlight, the same oceans, the same patient exchange of heat between water and air. The same conversations is continuing long after individual storms have disappeared. Perhaps that is the quiet perspective El Niño ultimately offers. The events that seem sudden in human life often belong to cycles that have been unfolding for centuries. The forces that shape tomorrow's weather have often been gathering for months, and the conditions influencing the future may already be moving silently beneath the surface of an ocean that appears calm to every passing ship. The Pacific asks for patience. The atmosphere rewards careful observation. And together they remind us that understanding the Earth is not about predicting every moment with perfect certainty. It is about learning to recognize the slow patterns that connect distant places, distant seasons, and distant lives into one living planet. As this story gently settles back into the quiet rhythm from which it began, the ocean continues its endless conversation with the sky. The trade winds will strengthen again. Warm water will gather, drift, and return. Clouds will rise where conditions invite them. Rain will find new paths across the continents. And somewhere beyond the horizon, beneath a surface that seems perfectly still, the next chapter has already begun. The ocean keeps its patient memory,